Now, bear in mind, your program is stored in different areas depending on your setup. On your desktop computer, the program can be stored on your hard drive or RAM or both, depending on how you have your computer set up. Your motherboard has an address bus and a data bus. The address bus for the utility circuits would be inside the microprocessor chip. Now, your program counter is a register, a memory location, just like any other register in the microprocessor. Now, while it automatically counts up with every clock pulse, it is a register that you can read and you can write to. So let's say your program was at line 40 in hex, and you actually wrote your program to look at one of the inputs to see if you pushed a button. It detects that you have pushed that button, and so you want to skip ahead in your program to say line hexadecimal A2. All you have to do is set your program counter to A2. Boom! The program counter is a register, which has an address, just like any other register, and you can simply write your program so that it addresses the program counter and loads that register with whatever number you want, just like any other register. So now, you can jump around in your program that way. For instance, usually if you reach the end of your program, you'll send it back to the beginning. Otherwise, it will run your program once and then stop all functions. Now, maybe that just happens to be what you want, and certainly you can. It's your program. You can do whatever you want. But most likely, you're going to want to run your program over and over again in a continuously running loop. So at the end of your program, you send a 00 hex to your program counter, and voila, you have just sent your program back to the beginning. So with this idea that your program is just going to run over and over again, think of your program as a routine. Part of that routine is to check to see if you pushed the big red button. You want your robot to start running around in circles screaming, "Ah, he pushed the big red button, run for your lives," or something to that effect. You have a series of instructions you want the robot to run when you push the big red button. When that big red button gets pushed, we want to leave our regular routine where the robot is doing the dishes. So the robot's normal routine is to sit there and do the dishes. However, we now want to leave our routine temporarily and run a subroutine. That subroutine might be run around in 3 circles screaming, "Ah, he pushed the big red button, run for your lives," and then go back to doing whatever it was doing before it ran that subroutine. So we call this subroutine. Our subroutine might be, say, 30 lines of code. And really, we can store that code at any memory address we want. So let's say we stuffed those 30 lines of code starting at hex address D5. We're running our original routine, and our program counter was at 0F when we hit the big red button. Here's what happens. The machine code instruction is call. When we call for a subroutine, one of the utility circuits, whom I will call Dan the Man, grabs the number out of the program counter and stuffs it into the stack. Now, the stack is like a shelf. The stack is a stack of registers, memory locations. Dan the Man then stuffs the address for the subroutine into the program counter, so now the microprocessor starts to run the program stored at hex address D5. At the end of the subroutine, you issue a command to return. Basically, you're telling Dan the Man you want to return from whence we came. So Dan the Man grabs the number off the stack and puts it into the program counter. You are now back running the original main routine right where you left off. Now here's the thing. Dan the Man has a stack of shelves. You can call a subroutine, and then while you're in the middle of that running that subroutine, you can call another subroutine. You call a subroutine. Dan the Man grabs the number from the program counter and stuffs it on the top shelf of the stack. He puts the address for the first subroutine into the program counter, and it starts to run the program at D5. Now, while my robot is running around in circles and screaming that I pushed the big red button, I hit the big orange button, which, I don't know, gets the robot to breathe fire, because, you know, breathing fire is an option while it's running around screaming about how you push the big red button. My fire-breathing subroutine was located at hex memory address F0. Our program counter is still counting off, so it had made it to hexadecimal DA when I hit the big orange button. So Dan the Man grabs the number on the top of the stack, sticks it on the shelf below it, grabs the DA from the program counter, and puts it on the top of the stack. He then throws F0, the address for our orange button subroutine, into the program counter, so the microprocessor now starts running the program located at hex F0. When it gets to the end of that subroutine, the program you wrote issues the return command. So Dan the man grabs the number that's at the top of the stack, puts it into the program counter. He grabs the number off the second shelf of the stack and puts it onto the top of the stack. The program picks up where it left off in the first subroutine. It gets to the end of that subroutine and tells Dan the man to return. Dan the man now takes the number off the top of the shelf, of the stack, and stuffs that into the program counter. We've now returned to where we left off in our main routine. So Dan the man's stack might only be, say, 10 shelves high. You can call a subroutine, then a sub-subroutine within that one, then a sub-sub-subroutine within that one, then a sub-sub-sub-subroutine from that one, and Dan the man will keep grabbing whatever number was in the program counter. He'll put it on the top of the stack and move the other numbers in the stack down one. Now, he only has 10 shelves in his stack. If you call 10 subroutines, no problem. But his stack is full. He's got no more storage room. He ran out of storage registers in the stack. So you then try and call an 11th subroutine, and Dan the man loses it. He snaps. He flips out and starts screaming at you, "I can't do anymore. I can't do this. Can't you see the stack is overflowing?" This is called a stack overflow error, and you might have even encountered such an error in your travels across the internet or programs which crashed on your computer. There's even a website called Stack Overflow using this common error as its homepage name. So the stack is an important bunch of registers which are used to store temporary numbers like program counters during subroutines, but the stack is usually limited. It depends on the microprocessor. I've seen them most commonly having a stack 10 levels deep. Now, a microprocessor, all it does is deal with numbers. That's really all it does. So it will perform math and number manipulation. Clinton's job, for instance, was what we call complementing. It changed all of the ones to zeros and zeros to ones. Now picture this for a second, if you will. Let's take a look at Clinton's register, which is 8 bits, 1 byte. Looking at just 1 bit, in order to do that, Clinton's circuitry has to have a NOT gate, but it needs to be combined with, say, an AND gate, because it needs to be driven by the clock cycle. Clinton has to control when the circuitry makes the conversion, so he can store the new number in a second register. So the second register also requires all of these gates like we did before, and then control lines to dump that register onto the data bus to pass it along to wherever it needs to go. So this is one simple function, and we need to multiply all of this circuitry by 8 because there are 8 bits in every byte that Clinton has to convert. Other utility circuits might have the hard circuitry to add 2 numbers together. So it needs to have 2 registers, 1 for each number to be added, which are connected by a whole mess of clock-controlled gates, which add the 2 bits, and then if there's a carry bit, it's just like if you add a 7 and an 8, you get a 5 and you carry the 1. Well, if you add binary 1 and binary 1, you get 0 and carry the 1 to the next most significant bit. All of this circuitry needs to have all the gates to do all that. There is a lot of circuitry involved here. So you can start to imagine the circuitry involved in multiplying or dividing 2 8-bit digits. It gets really big, messy, and complicated in a big hurry. If we wanted, we could build that huge array of utility circuits hooked up to every single register in the microprocessor. But why would we do that? The amount of space alone all that extraneous circuitry would take up would be huge. Rather, what the designers do is they make one specialty register, which has all of these complex digital circuits hooked up to it to perform all of the math functions. If we need to do math on a number that's stored in a register somewhere, we load that number from the register into the math processing register, do whatever mathematical function we want it to do, and then we can send the result to wherever, back into the register from whence it came, or some other destination in the microprocessor. This way, we only need one of all of those utility circuits that are so large and complicated. The specialty math register is called a bunch of different names. The Arithmetic Logic Unit, or ALU for short, is one name, and that makes a lot of sense for the name. But I've seen it called all kinds of different names. I got my first taste of machine code programming on the venerable Commodore VIC-20, which was one of the first home computers ever built. It was years ahead of its time and was the predecessor to the Commodore 64. Well, the very first machine code command we learned was LDA, load the accumulator. The accumulator was the name they gave the special math register. And the first command we learned was to load it with a number on which we would then perform some math functions, because it was the math register. So in the microprocessor we're going to use in the next lesson, they call it the working register. So whatever name it goes by, this specialty register is the register which has all of this complicated circuitry attached to it, so it can manipulate the number that it's given. Now, some microprocessors have more than one math register, but the number of these specialty registers is always a small number for the simple fact that each require huge banks of utility circuits that are so complicated and take up so much space and work to build. All right, are you exhausted yet? Because now we're going to dig into microcontrollers.